Dear learners, welcome to the course Electromagnetic Fields. In this video, we are going to talk about electromagnetic model. Generally, model means a mathematical representation of a series of measurements, experiments, observations, calculations, assumptions, approximations and simplifications. Electromagnetic model is a mathematical representation of electromagnetic fields or phenomena. There are two approaches used to develop electromagnetic model. These approaches are inductive approach and deductive approach. We are going to discuss inductive and deductive approach. What is inductive approach? In using inductive approach, one follows the historical development of the subject, starting with the observations of some simple experiments and inferring from them laws and theorem. It is a process of reasoning from particular phenomena to general principles. And the second approach is deductive approach. On the other hand, postulates a few fundamental relations for an idealized model. The postulated relations are axioms from which particular laws and theorems can be derived. Three essential steps are involved in building a theory on an idealized model. First, some basic quantities are defined. Second step, the rules of operations of these quantities are specified. The third, some fundamental relations are postulated. These postulates or laws are invariably based on numerous experimental observations acquired under certain conditions and synthesized by brilliant minds. In a like manner, an electromagnetic theory can be built on a suitably chosen electromagnetic model. In this video, we shall take the first step of defining the basic quantities of electromagnetics. The second step, the rules of operation, encompasses vector algebra, vector calculus and partial differential equations. The fundamentals of vector algebra and vector calculus will be discussed in next videos. The third step, the fundamental postulates, will be presented in the next part in the electrostatics and the magnetostatic fields and electromagnetic fields respectively. The quantities in electromagnetic model can be divided into two categories: source quantities and field quantities. The source of an electromagnetic field is invariably electric charges at rest or in motion. However, an electromagnetic field may cause a redistribution of charges which will in turn change the field. Hence, the separation between the cause and the effect is not always so distinct. We use the symbol Q to denote electric charge. Electric charge is a fundamental property of matter and exists only in positive or negative integral multiples of the charge on an electron. The principle of conservation of electric charge, like the principle of conservation of momentum, is a fundamental postulate or law of physics. It states that electric charge is conserved, that is, it can neither be created nor be destroyed. This is the law of nature and cannot be derived from other principles or relations. Its truth has never been questioned or doubted in practice. The principle of conservation of electric charge must be satisfied in all times and under any circumstances. We define a volume charge density ρ v or simply ρ as a source quantity. Ρ v is equal to del q by del v as limit del v tends to 0. The unit for volume charge density is coulomb per meter cube. In some physical situations, an amount of charge del q may be identified with an elemental surface del s or as an element of length del L. In such cases, it will be more appropriate to define surface charge density rho s or line charge density rho L. Rho s is equal to del Q by del S as limit del S tends to 0. Unit for surface charge density is coulomb per meter squared. Similarly, line charge density is the ratio of amount of charge per unit length, that is a small amount del L, as limit del L tends to 0. Unit for line charge density is coulomb per meter. Next, current is another source for electromagnetic field. Current is a rate of change of charge with respect to time, that is I is equal to dq by dt. Unit for current is amperes. In electromagnetics, we define a vector point function volume current density. Simply it is J vector, which measures the amount of current flowing through a unit area normal to the direction of current flow. It is represented as J vector. So bold face, it represents it's a vector quantity. Unit for volume current density is ampere per meter square. For very good conductors, high frequency alternating currents are confined in the surface layer as a thin current sheet instead of flowing throughout the interior of the conductor. In such cases, there is a need to define a surface current density Js, which is the current per unit width on the conducting surface normal to the direction of current flow and has a unit of ampere per meter. Next, we are going to discuss about the field quantities. There are 4 fundamental vector field quantities in electromagnetics. These are electric field intensity E vector, electric flux density D vector, magnetic field intensity H vector, magnetic flux density B vector. The definition and physical significance of these quantities will be explained in later videos. So next we are going to discuss about fundamental SI units. The units which are independent, chosen and not dependent on any other units are called fundamental units. These are also called base units. The fundamental units are quantities, length, mass, time, current. Unit for length is in meters, unit for mass is kilogram, unit for time is second, unit for current is in amperes. In our electromagnetic model, there are 3 universal constants in addition to the field quantities which are listed in this table. These universal constants are velocity of light in free space. It is represented as C symbol. Value for velocity of light in free space is 3 × 10 power 8 meter per second. Another constant is permeability of free space, represented as mu naught. Value for mu naught is 4 pi × 10 power minus 7 Henry per meter. And another universal constant is permittivity of free space, which is represented as epsilon naught, 1 by 36 pi × 10 power minus 9 farad per meter. The two constants epsilon naught and mu naught pertain to electric and magnetic phenomena respectively. Epsilon naught is the proportionality constant between the electric flux density D vector and electric field intensity E vector in free space. D vector is equal to epsilon naught E vector in free space. Similarly, H vector is equal to 1 by mu naught B vector in free space. The value of epsilon naught and mu naught are determined by the choice of unit system and they are not independent. In the SI system, which is almost universally adopted for electromagnetic work, the permeability of free space is chosen to be 4 pi × 10 power minus 7 Henry per meter. And value for epsilon naught is obtained by using the relation epsilon naught is equal to 1 by C squared mu naught. That substitute the values of C and mu naught here, we will get 8.854 × 10 power minus 12. So the permittivity of free space is 8.854 × 10 power minus 12 farad per meter. Now that we have defined the basic quantities and the universal constants of the electromagnetic model, we can develop the various subjects in electromagnetics. So, you could understand the basics of electromagnetic model and what are all the source quantities and the field quantities in electromagnetics. Thank you.